Hello, everyone. Today we're going to be studying the uses and the dangers of radioisotopes. Things that definitely matter with this lecture are there's a quiz associated with this lecture. So if you're watching this video at night, the day before class, then you have a quiz tomorrow. It'll be on Half-Life, though. And yeah, so today we're just going to we're going to look at dating and the medical applications and the use of irradiation for food preservation. And all of those things are related to the uses of radioisotopes. There are also risks as well, and we'll go over those. There is a bookwork associated with this lesson. It's up here. It's like reading on pages 226 to 228 and answering questions 48 to 57 on page 228. There's no explanations necessary, and this will be due next class period. So be prepared to get started on those in class tomorrow. But we will do sort of our typical our typical routine of we'll do a do now, which in this case will be the quiz. And then we'll go straight from there and we'll do the pair up, and which you'll need to copy down, and then you'll start the bookwork. So that'll be basically class tomorrow. So definitely have another piece of paper in your classwork section of your binder that has the do now copied on it, which is a quiz today, and the pair up copied down, and then after the pair up have this bookwork title copied down, so we have that. Okay. All right, dating. So all living things are organic beings. And a lot of you guys have a definition of organic that matches the definition in the grocery store, which is that it's all natural. But what you might remember from living environment is that an alternate definition for organic is an organism that contains carbon and hydrogen. So the reason why I'm bringing that up right now, this definition of organic that you may have learned in biology, is because there are different forms of isotopes, or different forms of elements that we call isotopes, and some of those isotopes are stable, while others are unstable. There are lots of ways to think about how one isotope would be stable versus unstable, but this is an example of one. It's carbon-14. Now, most carbon atoms are carbon-12, but some of them are carbon-14, and those ones that are carbon-14, those are actually radioactive, and that means they have a half-life. I believe their half-life it's above 5,000 years, like 5,860, something like that. And that means that a small portion of the atoms in any in any organism, a small portion of those carbon atoms will be carbon-14. And that means that all living things have some portion of their bodies which is made of a radioactive isotope, carbon-14. And since we know how much carbon-14 should be in a living thing, and we also know the half-life of carbon-14, you can use those two pieces of information to figure out how old a fossil is when it perished. So basically, it's some fairly simple math, just based on the half-life that we've been learning. You just need to, in any kind of living or once living thing, like for instance, a fossil from this snail, you just need to look at the ratio of carbon-12 to carbon-14 that's in the snail's, in this case, shell. So if we look at the ratio of carbon-12 to carbon-14 in the snail's shell, we'll be able to tell basically when the snail died. The idea is pretty simple. We know what the ratio of carbon-12 to carbon-14 is in the universe. So if the snail were just very recently died, then the ratio of carbon-12 to carbon-14 in its shell would be very similar to the ratio of carbon-12 to carbon-14 in the universe. Basically, if the snail is alive and it's eating food and stuff like that, then it's going to have the same ratio of carbon-12 to carbon-14 as everything around it. That's the theory. But when the snail dies, it stops eating food. It stops taking in more and more carbon to replenish that ratio. And from that day on, the amount of carbon-14, that's the radioactive one, starts to drop. And the reason for that, so it's going to start to decrease. The reason for that is that the carbon-14 is unstable, it's radioactive, and it naturally decays into, I believe, nitrogen-14, and I think it releases beta particles. I'm not sure, but in any case, that amount of carbon-14 drops, and you would notice that if you came back a few thousand years later and measured the amount of carbon-14 in the snail's shell, you would see that the amount of carbon-14 is quite a bit less than what you would expect from a living snail, and that's because of radioactive decay. Now you can use the difference in how much carbon-14 you have left versus how much you should have had. You can use that difference to calculate how long the organism has been dead. So let me answer this question. So when something dies, it stops taking in carbon. What will then happen to the amount of carbon-14 in the body of the dead organism? Think of your answer, and I'll write it in for when you come back. So you probably wrote down it decreases, and you are correct about that. Next question, it says, how old is a fossil that has 1/4 the amount of carbon-14 that a living thing has? So if it has 1/4 of the amount, I think the first thing you should think about is how many half-lives has this fossil been through? Think of your answer to that question and pause the video, and I'll have the answer when you come back. So to me, I know that it's been through 2 half-lives, and if you need a quick explanation of that, it's just that 1/2 times the fraction 1/2 will give you the fraction 1/4. They said in the question that we had 1/4 remaining, and that means that it's been through specifically 1 half-life and another half-life to give you a fourth. Now, it actually says how old, so they want the answer to be in years. And think about the way that you would take the number of half-lives and figure out how many years that's been. Pause the video and I'll have the answer when you come back. All right, so I did a couple of things while you had the video paused. The first thing that I did was I sort of set up the way that's going to be solved. I said I took the number of half-lives and I'm multiplying it by a number of years. But where did I get this number of years? I got that from table N, so you do need to know that. And you should always use table N whenever you need to know a specific number of years in a half-life for a particular isotope. This one's carbon-14, and I'm using carbon-14 because it's a fossil, and fossils would have carbon-14. And I looked it up on table N, and I was able to find that carbon-14 has a half-life of 5,715 years. It's a little bit different than my guess from earlier. And I need to multiply the number of half-lives by the length of a single half-life, so I'm going to multiply 2 by 5715, and I'm getting 11,430 years. So that is my estimate for how old the fossil would be. Now my next question is actually not focused on carbon-14, but you should know on this slide that whenever you have an organic thing, if it was ever alive at any point, then it contains carbon, and it therefore contains carbon-14 as well, and so you use carbon-14. But there are plenty of things that we want to know their age and are not alive and were never alive. Think about rocks, for instance. So we can still date those, but we wouldn't use carbon-14 because those rocks, for instance, probably don't even have carbon in them. So we would use other elements that are more common in those inorganic things. And for inorganic remains, like for rocks, for instance, we tend to use uranium-238. It decays into lead-206, whereas carbon-14 was decaying into, I believe, nitrogen-14. But this guy is decaying from uranium-238 into lead-206, and it's used for dating rocks and other geologic structures. So if you see like geologic structure, they're talking about rocks and stuff, and you would use uranium-238. There is a little rhyme I do in my head for this, and it's that uranium-238 is to date. So aside from dating, there are some really great other uses for radioisotopes. One of them is in medicine. There is a really common use for a radioisotope is to use it as a tracer. A tracer is actually in a lot of ways what it sounds like. It's a radioisotope which is utilized in order to trace the route that certain elements might take in nature or even in the human body. So we can use, for instance, iodine-131. It's in the form of a pill, and the patient takes it, takes the pill of iodine-131, which is a radioactive isotope of iodine. They swallow it, and most tissues in the body don't like iodine, and so they don't absorb it and they don't collect it in the tissue. But there is one organ in the body which does really use iodine a lot, and tries to absorb it and hold on to it as long as possible. And that would be the thyroid gland. So the thyroid is up here near your larynx. And it's an endocrine gland. It releases hormones that regulate metabolism. But in any case, it really needs iodine. And if you give a patient iodine-131, the thyroid doesn't know it's radioactive iodine, it just knows it's iodine, and it absorbs it. So if you were then to take a radiation image of the person's body, you would see that the radiation has collected in the thyroid. And that can be really useful in two ways. The first way is then you get an image of the thyroid, which you wouldn't have had before. And secondly, the radiation in that iodine can damage parts of the thyroid, which may sound like a really bad thing, but if, for instance, you have thyroid cancer, then damaging those cancer cells is actually an advantage. So sometimes we use iodine-131 to identify thyroid disorders through imaging, and sometimes we use it to treat thyroid disorders by purposely killing the cancer cells in the thyroid. There are other radioisotopes that you should know. Now, you do need to know iodine-131, so keep that in your notes. But you also need technetium-99 in your notes. Technetium-99 is great at identifying tumors, so it's really just for imaging. But we'll give technetium-99 to a person, and we've learned that tumors contain cancer cells, and cancer cells tend to absorb technetium-99, so that means that if you take an image of it, then you will see the tumors more than other tissues. Other ones you need to know are cobalt-60 and cesium-137. Both of those particular isotopes are used in radiation therapy. So cobalt-60 and cesium-137, we'll use those to create radiation, and then we'll use that radiation and we'll aim it at tumors and kill the tumors on purpose. So you might use technetium-99 and cobalt-60 together, for instance. The technetium-99 will identify where the tumor is, and then the cobalt-60 will release radiation that you can point at the tumor to try to kill it. Now, here's something that you need to know. In terms of half-life and ease of elimination from the body, there are good qualities that medical radioisotopes have. And I want you to think about the half-life of a good radioisotope and ease of elimination of a good radioisotope, and pause the video, come up with how you think those should behave, and then I'll write the answer when you come back. Alright, so here's my answers. Firstly, it needs to have a short half-life, and that means that if it has a short half-life, it's going to decay quickly, meaning it's, half of it's leaving in a short time period. And secondly, it needs to be easily eliminated, and not to be crass, but it just means that your body's able to pee it out really quickly. Examples of elements that you would never use because your body wouldn't pee them out very fast, are elements like calcium, for instance, because instead of your body eliminating calcium, it tends to want to hold on to calcium. So any of those vital nutrients and those vitamins that we need, we wouldn't use those. We wouldn't use a radioactive isotope of one of those. Here's another really interesting benefit of radiation. It's in the practice of something called irradiation. And irradiation is when we will purposely expose fresh fruits, fresh vegetables, and fresh meats, and we'll purposely expose them to radiation. It sounds really bad, but it's actually kind of helpful because that radiation, well, so all this stuff is dead anyway. It's already dead, so you're not going to, kill it. It's already dead. But there are some things that are living that are on this, and those are bacteria and other microorganisms, and those are responsible for making these foods spoil. So what we tend to do is we'll spray these foods with radiation, like gamma rays, for instance, and it'll kill all the bacteria on the food, and then that food will stay fresh for longer. It's a really interesting use of radioisotopes, and since it's gamma rays, it doesn't stick to the food, so you're not going to be eating radiation or anything afterwards. So it can be really helpful. So I tossed in some answers to my questions. The first thing is that the strawberries in this example are going to remain fresh and delicious because the bacteria were killed by the irradiation. Gamma radiation is the best choice for food irradiation because it's pure energy and therefore it will not stick to food. And this isn't actually a very popular method of food preservation in the United States because of miseducation. People associate the word radiation with death and cancer in an irrevocable way, and they're not able to see that bullet number 2 is still applies. All right, here's another benefit and also a risk of nuclear radiation. So nuclear power is both a benefit and a risk, in my opinion. So we use nuclear power in power plants, and basically we use the radiation, it makes heat, and we use that heat to power turbines and then make electricity. So a possible advantage of using nuclear fuel is that you get electricity, but I don't know if you noticed this, but there's no fossil fuels involved here. It's all nuclear. So you get electricity, but without fossil fuel disadvantage. But nuclear power plants are built very carefully with lots of really smart people, but sometimes they don't work out. Sometimes there's an accident, and when an accident occurs in a nuclear power plant, it's usually not something that can be fixed. And it will lead to the destruction of the power plant because of all the nuclear power inside. One of the worst examples I can remember was one that happened in Ukraine, I believe back in the 80s. And a nuclear power plant went through a meltdown, and it released a ton of radiation into Ukraine, and that radiation escaped into the atmosphere, and it was spread over the entire planet. We were measuring radiation levels in the United States as a result of this accident in Ukraine that were extremely high. So we know that a nuclear power plant disaster in one part of Earth affects all parts of Earth. So obviously there's lots of different things that are really bad about that. You can get DNA damage, mutations, so on and so forth. And that means that it's also a risk as well as a potential benefit. So maybe it's good, maybe it's bad. There are arguments for both, and you should know both of those arguments. So here's my next question. Nuclear power uses fission, which produces waste products with long half-lives. Why is this bad? So if you have a really long half-life, that means that if that waste product escapes into the environment, that it's going to remain radioactive for a long period of time. That's why it's bad. So yeah, you could just write in remains radioactive for a long time. And this also brings up something we had spoken about earlier when we talked about fission and fusion, but we really hope that someday we can work out the specifics of how to use fusion to create nuclear power, because if you were to use fusion, you would not get these waste products with long half-lives. You would get stable, safe waste products like helium. So yeah, we really want to do fusion, but we haven't figured it out yet, but we would love it. All right, so I've gotten us to the pair up. I need you to make sure you have this pair up copied down on loose leaf. Don't forget to go back to the beginning of the video and copy down the homework assignment underneath the pair up, because we'll use that bookwork in class, and I see you guys next. And also copy down this summary. In the summary, we'll have and part of our exit ticket will come from that.